Good evening to all the dear participants.
Good evening, sir.
Sir, am I audible, sir?
Yes, sir. Yes, sir. You are audible.
Oh, okay, sir. Okay. Thank you very much, sir. All right, dear participants, let's begin today's sessions. Today we have two sessions. The first one to begin with, doping strategies and charge carrier transport in nanocomposites and atomic thin layers by Dr. M.D. Kamath sir. And the next session will be from Dr. Srivastava Suribhi from Chile. And to begin with, it would be my great honor and privilege to introduce today's speaker to all of you. The first session is from my best friend, Dr. M.D. Kamath sir. Dr. Kamatki did his post-graduation in the year 2001 under solid state physics. He completed his MPhil in the year 2003 with a dissertation titled Diffusion Thermopower in GIN Quantum Wells and PhD in the year 2010 with the title Some Thermoelectric Properties of Two-Dimensional Semiconductor Structures. His research areas includes thermal transport in semiconductor nanostructure, thermal conductivity, thermopower, thermoelectric figure of merit, transport properties in graphene and 2D structures, photoluminescence properties of metal oxide nanoparticles and polymer nanocomposites, and molecular dynamic simulation. He is also well versed with computational technologies like MathCAD, Mathematica, and LAMPS. He has certain academic achievements. Among the most prominent them are Adhyabuk Bhushan Award in the year 2017 from Karnataka University Vibhaga Unit, Dr. D.C. Paute Fellowship to Cambridge University, Cambridge, UGC-sponsored minor research project entitled Thermoelectric Properties of Graphene Nanostructure. He has contributed to set up MSc Physics Laboratory at SS Government First Grade College PG Studies Center at Nargund, and one student completed his PhD under the guidance, and currently one student is pursuing PhD under the guidance of Dr. M.D. Kamath sir. As of now, sir has presented 39 research articles in various reputed journals and more than 30 papers in various international conferences. As I know, he is one such researcher who has great interest in both theoretical as well as experimental sciences. With these brief words, I now welcome Dr. M.D. Kamath sir to brief about today's session. Sir, present.
Thank you, Dr. Samir. I hope I am audible.
Yes, sir, you are audible, sir.
Thank you. First, I thank the organizer for giving me an opportunity to share our work. And also I thank Dr. Samir for his nice introduction. Today I will be talking on doping strategies and charge carrier transport in nanocomposites and atomic thin layers. I will start with what the doping is, and then different types of doping in nanomaterials, and then the reports that are in literature, and then finally I will present our work wherein we have doped polymers with nanomaterials. We all know the concept of doping. Doping is intentionally introducing an impurities into an host lattice. For example, when we dope or introduce phosphorus in silicon, phosphorus being pentavalent and silicon being tetravalent, so the phosphorus forms a tetravalent bond and one bond remains vacant. So we'll have an extra electron in the lattice. This increases an electron concentration. The purpose of doping initially to increase the carrier concentration. So in case of a silicon or germanium, to have an N type of semiconductor, we dope with tetravalent metals and pentavalent. To have an P type semiconductors, we use trivalent atoms. The most prominent being boron for p-type semiconductors, and for n-type semiconductors, phosphorus is a dopant. So why doping is important? So the intrinsic semiconductor conductivity is very less. The first thing is, and we cannot have the transistor without doping. We need a p-type material as well as n-type materials. So doping becomes very important. By controlling the type of concentration of the dopant, one can precisely tailor the electrical properties, optical properties of the material for specific applications. Besides the increase in the concentration of the carriers, doping also modifies the band structure, which already we all know it. Doping is significant in nanostructure because it modifies the electrical, optical, and chemical properties, which we can use for specific applications. For example, the modulating electrical conductivity by doping, the primary reason is to have a N-type or P-type semiconductors, wherein the number of free carriers are increased, significantly enhancing the material's conductivity. The other key reasons for doping a nanomaterial includes tailoring the optical properties, enhancing catalytical activities, introducing the new physical properties, including that of the mechanical properties. Doping becomes very significant in case of the nanostructures as it modifies the electrical, optical, and chemical properties of the nanomaterial. When conducting or any material is doped with the nanomaterials, the properties of nanomaterials as well as the conducting materials are combined, which found a vast amount of application in different fields, such as solar cells and thermoelectricity and sensors. Doping is necessary in nanomaterials because it allows us to tune and control the properties. The essence of doping provides the flexibility to engineer nanomaterials with precise application-specific properties. There are broadly two ways to dope the material. One is in situ doping, another is post-synthesis doping. In situ doping, there are again subsections. A chemical vapor deposition, which is a common method, especially for nanowires and 2D materials like graphene, where the precursor gases containing the dopant atoms are flowed into the reaction chamber during material synthesis. Doping concentration and the location can be controlled by adjusting the gas flow rates and temperature. Other very cost-effective method is colloidal synthesis or a solution growth, which is widely used for quantum dots and nanoparticles. Dopant precursors are added to the host precursor solution. The reaction temperature and timing of dopant injections are critical for successful incorporation of the dopants. The other method is the hydrothermal or sol-gel method. This is a solution-based technique, allows the production of nanoparticles with controlled morphology and tunable ion doping through careful control of reaction environment like temperature, pressure, and the pH of the solution. The other method is the flame spray pyrolysis. It's a rapid combustion method wherein using a liquid precursor and at a high temperature, flame is used to synthesize homogeneous crystalline doped nanoparticles. So there are other techniques also, the post-synthesis doping techniques, wherein the ion implantation, which is usually done through MBE. Dopant ions are ionized, accelerated into a nanomaterial crystals at high energies and embedded below the surface. This offers precise control over the dopant depth and concentration profile. In case of the thermal diffusion, the nanomaterials is heated in an atmosphere containing the dopant atoms, which then diffuse into the lattice. This can be combined with spin-on dopant techniques where the dopant controlling liquid film is applied to the surface before heat treatment. There are surface charge method, which involves a chemioabsorption or a physicoabsorption of organic molecules or metal particles onto the surface of the nanomaterials. The prominent being electrical doping. It's a non-conventional method used in nanoscale devices, modeling where the potential difference is applied across the device. Its bias voltage is applied across the device, effectively modulating the charge carrier concentration without adding the foreign atoms. These are some major techniques wherein we dope the nanomaterials or any bulk materials. So I will share idea of modulation doping in heterostructure. Heterostructure is a device where material is sandwiched between two wide band gap materials. For example, the gallium arsenide. Gallium arsenide, when sandwiched between aluminum gallium arsenide, aluminum gallium arsenide band gap is more than that of the gallium arsenide. So the band engineering takes place and the heterojunction is formed. And when we sandwich gallium arsenide between two aluminum gallium arsenide, so effectively we are joining the two heterojunctions. When we join the two heterojunctions, it forms a well-like structure, and that we call it as a quantum well. This is a well-like structure. Now what we can do here is, so this is a gallium arsenide. Typically it will be of the order of 1 to 100 angstrom. Then we will sandwich it between two aluminum gallium arsenide. If it is a heterojunction, only one aluminum gallium arsenide. And this will act as a spacer, and will on that another layer will be formed. this aluminum gallium arsenide, where we dope it. So modulation doping is a technique in a semiconductor such that the free charge carriers are spatially separated from its donors. When we separate something like that, here the donors are there. There are the electrons from these donors. They lose energy and comes and sits in this junction. So in quantum world, the donors are here and the electrons wants to lose their energy because they want to sit in the lowest possible energy, and the lowest possible energy is somewhere here. They lose energy and comes and sits and forms a two-dimensional electron gas. What happens when the two-dimensional electron gas, which is far away from its donor impurities, this eliminates a scattering from the donor. So therefore, the modulation doped semiconductors have very high carrier mobilities. For example, the modulation doped gallium arsenide has 3 times compared to the uniformly doped. This is uniformly doped and this is bulk gallium arsenide, which has got almost a 3 times mobility. Around 100K, the mobility has increased by 3 times. The doping enhances, in case of gallium arsenide, the mobility as well as the electrical conductivity. Therefore, the doping becomes significant when we approach at the nanoscale. This is another example. This is an example of gallium nitride quantum well and gallium nitride quantum well heterostructure, wherein the mobility has increased by 3 times. Recently, there has been an interest in the two-dimensional materials. Graphene is a one which is a first perfect two-dimensional structure, which is a single layer of graphite. It has a honeycomb structure, a hexagonal structure, where the carbon atoms are arranged in an hexagonal way. And we all know that graphene has got a very high electrical conductivity and thermal conductivity. By directly introducing in foreign atoms through a chemical vapor deposition, a CVD approach, wherein we can produce a graphene films with a high doping uniformity and stability. However, in graphene, which is a very degenerate system, already it has got a large electron concentration, and the electrons in a graphene are massless. They are Dirac fermions. If we dope this graphene by an impurities, then the mobilities are greatly reduced because of the charge carrier scattering. For example, if we dope a graphene with a nitrogen, a uniform distribution of a dopants will reduce its carrier mobility by at least 5 times. Instead of a single substitutional N, if we dope as a cluster of nitrogens, then its mobility is atypically high. But still it is less than the intrinsic mobility, and the intrinsic mobility of the graphene is around 12,000 centimeters square per volt second. So to enhance the mobility, doping is not a great idea or a good idea in case of the graphene. But to enhance the electrical properties of compound semiconductors like gallium arsenide and gallium nitride, doping is significant and doping is a very good idea. But in case of graphene, the doping is not at all a good idea to enhance the electrical properties. So inspired by the invention of the graphene, researcher has invented the other two-dimensional materials, namely the transition metal diagonalized layered materials, which are seen at present an alternative for graphene with potential applications in electronics, optoelectronics, and the high-speed devices, including the thermoelectric devices. These layers, monolayers, or the few layers, are van der Waals bounded layers materials with chemical formula MX2, where M is a transition metal and X is dichalcogenide. The importance of these MX2 layers comes because they possess a finite band gap varying from 1 electron volt to 3 electron volt, in contrast with that of zero band gap graphene. These MX2 layers have already proved they are the best, they can be a best thermoelectric materials. And this is a structure of MX2 layers wherein the M is sandwiched between two X layers. These layer atoms are having covalent bonds, but the bond between these two layers is a van der Waals bonds. Now I'm sharing a report of these MX2 layers. This is mobility as a function of electron concentration. One can see that the mobility increases monotonically up to, for example, if I take a case of MOS2, the mobility increases monotonically up to a particular point and then it starts decreasing. This is probably due to the electron-electron scatter. Now the dashed line shows the mobility of unstrained. The straining is done through undoping. Whereas this red dashed line shows the mobility, overall mobility, wherein the tensile strain is 5%. When we dope the material with the particular dopant, it supplies the charge carriers as well as it introduces a strain in the lattice. Sometimes this strain reduces the mobility or electrical properties, but sometimes this strain becomes important to increase the electrical properties of these MX2 layers. Therefore, the doping depends on which material we are using and for what purpose we are doping the material. So therefore, the doping becomes very significant. Now, I will share our work, theoretical work, as well as some experimental work on nanocomposites, how the doping affects the thermoelectric properties. So I will briefly introduce the thermoelectric properties. So when there is a temperature gradient, if I take a thin layer and if we maintain them at two different temperatures, this end is in hot, this end is in cold, so that there is a temperature gradient. So in this temperature gradient, the electrons as well as the lattice vibrations, which we call it as phonons, flow down the gradient. In doing so, they will carry the heat energy. And this heat energy carried per unit area per unit time is directly proportional to the temperature gradient. So the ability of a material to carry a heat, we call it as a thermal conductivity, and the heat is carried by both electrons as well as lattice vibrations. Though, therefore, we have electronic contribution to a thermal conductivity. This is a thermal conductivity carried by an electron, and the contribution from phonons to carry this energy. The electron thermal conductivity is sensitive to the composition of the material as well as the scattering centers and the electron concentration. And lattice thermal conductivity is sensitive to a phonon scattering as well as the material structure. When we have a temperature gradient, obviously the electric field is set up. More the temperature gradient, more will be an electric field. So therefore, the electrons also diffuse under the influence of temperature gradient as well as electric field which is set up inside this material. This gives rise to a thermopower. The diffused electron electric field gives rise to a diffusion thermopower. Also, phonons will diffuse because of the temperature gradient. They may give an extra momentum. Suppose that this electron is moving in this direction and another phonon comes and hits it. So that this electron will gain an extra momentum. And this contributes to an phonon drag thermopower. And this phonon drag thermopower is significant only at liquid helium temperature or less than 20 K. After 20 K, the phonon-phonon scattering becomes more prominent. So therefore, the momentum transfers becomes negligibly small. At room temperature, the contribution of diffusion thermopower is more. In case of semiconductors, the lattice thermal conductivity is dominant at room temperature compared to the electronic thermal conductivity. So another thermoelectrical property is electrical conductivity, which is governed by Ohm's law as long as this electric field is small. In the presence of electric field, the electrons will drift, giving rise to an electric current density, which is directly proportional to the potential difference per unit length, that is electric field. So the mobility is related to electrical conductivity. What we have done is we have taken a series of MX2 layers and applied the Boltzmann transport formalism. We considered the phonon scattering by boundaries, impurities, and phonons, and electron scattering by acoustic phonon, charged impurities, as well as remote impurities. And we have evaluated the thermoelectric properties, namely thermopower, electrical conductivity, as well as thermal conductivity. And the thermoelectric performance of a device is quantified by a figure of merit. It's a dimensionless parameter ZT, which depends on these three. The MX2 layers have higher ZT. The report says it has got a higher ZT. Therefore, we have investigated the thermoelectric properties. What we have seen here is, in case of MX2 layers, if we dope, if we increase the concentration of an electrons via doping, we should remember it's not staining, via impurity doping, then the S square sigma, the product of square of the thermopower and electrical conductivity, monotonically decreases. Remember, when we dope, the electrical conductivity of these MX2 layers monotonically increases. When we dope, the Fermi energy increases, and this Fermi energy reduces this thermopower. Also, it increases an electrical conductivity K. So therefore, the ZT reduces. we have proved that in case of the MX2 layers, the undoped MX2 layers possesses high ZT compared to doped MX2 layers. So therefore, if we are looking for thermoelectric properties of an MX2 layers, for example, if we are looking it for as a cooling device, then the doping is not a good idea. Suppose if we are looking for just an electrical conductivity, wherein this electrical conductivity increases monotonically with electron concentration, then the doping idea is a correct one. So therefore, the doping has to be selective. For which purpose we are using the material, that should be a clear one. If it is for a thermoelectric performance, for MX2 layers, the doping is not the correct idea. Now, I will share now our experimental work. The structural and optical properties of polymethyl methyl acrylate, which is a polymer doped with zirconium oxide. So when we dope the polymethyl methyl acrylate with zirconium oxide, it forms a nanocomposite. Polymethyl methyl acrylate is an amorphous thermoplastic. It belongs to an acrylate family. It has got good tensile strength and excellent optical transparency. And ZrO2 is a wide bandgap semiconductor which comes in different crystalline phase. So the idea was to check what happens when we dope polymethyl methyl acrylate with zirconium oxide. The motivation was twofold. The first is to check its optical properties like absorption as well as photoluminescence emissions. And the next idea is to check its mechanical strength. What we did is we have synthesized polymethyl methyl acrylate and zirconium oxide ZrO2 nanoparticles by chemical co-precipitation methods. These are the reagents we have used in the synthesis. So there are different methods to synthesize the nanomaterials as well as the polymers. So to synthesize the ZrO2 nanoparticles, we have used co-precipitation method. So this is the simple experimental procedure or the scheme of an ZrO2 synthesis, wherein we have taken zirconium sulfate and NaOH in 1:4 ratio, and we mixed. When we mixed, the white color precipitate was formed, and then we washed with the deionized water to remove any impurities, and then we obtained a ZrO2 nanoparticles. And the obtained ZrO nanoparticles, by this method, the particle diameter varies from like a 10 nanometer to around 16 nanometer. And by using solution casting method, so we have prepared an polymer composite. This is a typical procedure of polymethyl methyl acrylate and ZrO2 nano composite film. So we have introduced ZrO2 nanoparticles in PMMA with a weight percent of 3, 5, and 10. In a typical procedure, we took 1 gram of polymer, which we dissolved it in 100 ml of chloroform because it dissolves in chloroform, and a different weight percentage of ZrO2 nanoparticles were dispersed in 50 ml of chloroform. Here we have given the weight in grams. Then we mix the solution of ZRO nanoparticles into the polymer solution dropwise under constant stirring. The mixture solution was transferred to a dish, and we kept it for 72 hours to evaporate solvent slowly at room temperature. And finally, we obtained polymer and nanoparticle composite, SPMMA and ZRO2 nanocomposite film. Here, I will show you the procedure. This is the films. These are the films which are doped with different weight percentage of ZRO2. So this we have done in our PG laboratory, and this work is done by our MSc students. So the one with 3% we are denoting it by P1. The one with 5% of ZRO2 we are denoting it by P2. The one with the 10% of ZRO2 polymer we are denoting it by P3. Now, what happens when we dope with ZRO2? This is the excited pattern of undoped, I mean pure polymethyl methacrylate film, which shows an amorphous nature. When we dope it with 1%, that's a P1, and 3%, that's a P2, we can see a small peaks are coming out. This shows that at 30 and at 50 degree, that's a 2 theta, these peaks are indexed to 101 and 112 crystal planes of ZRO2. This shows that we have successfully incorporated or doped the polymethyl methacrylate with ZRO2 nanoparticles. This is the bulk materials, and we are doping or adding nanoparticles into an bulk materials. For 5%, clearly we can see a crystalline peak, and other peaks also comes. So the extra peaks at 2 theta is equals to 30 degree, 35, 50 and 60 were indexed to in various planes of ZRO2, which are well consistent with the JCPDS data. This shows that by a simple solution casting method, we can introduce a nanomaterial into a polymers or in any other materials. Now, what is an effect of this doping on the optical properties? We can clearly see that the absorption edge shifts. There is a red shift. A slight red shift is noticed. This means the ZRO2 nanoparticles are well into the lattice sites of polymer. Then using these absorption data, we plotted a talk plot wherein we have estimated the band gap. So clearly the band gap has reduced from 5.18 electron volt to 5.06 electron volt. So that means when you dope the ZrO2 in PMMA, its band gap is redshifted. Since PMMA is widely used for denture applications, its photoluminescence properties are very important. The one with blue line, the blue line is for P3 sample, which exhibits a much higher photoluminescence. The intensity of photoluminescence is much more than that of the pure PMMA. Also, there is a shift in the peak values of PMMA. This is attributed to an interaction of ZrO2 nanoparticles with carbonyl group of PMMA. I hope I am audible. Hello.
Sir, you are audible, sir.
Okay, thank you.
Go ahead, sir.
The main idea of our work was to check if we dope the PMMA with ZrO2, what happens to its mechanical strength. The idea was for denture applications, we need to have an higher mechanical strength as well as higher photoluminescence. These two has to be combined. The shining is important for denture applications as well as the mechanical strength was important. Then what we noticed is we measured a stress after straining it. What we noticed is the P2 sample. Here we have tabulated the yield stress, yield strain, break stress, and break strain. What we have noticed is the PMMA has got lower stress. It can hold lower stress as well as lower strain. Whereas the P2 sample, the one which is doped with 3% of ZrO2, exhibits higher stress. That means it can hold the higher strain. This shows that the doping of ZrO2 in polymethyl methyl acrylate greatly enhances the mechanical properties as well as the photoluminescence properties. Now, our work has showed that if you dope the PMMA with ZrO2, then its mechanical strength increases. That is a very good idea for denture applications. Similarly, we have worked. What happens if we dope PMMA with simultaneously with ZrO2 as well as a graphene oxide? We all know that the graphene oxide or reduced graphene oxide is similar to that of graphene, and already we have studied the composite, that is polymethyl methyl acrylate as well as ZrO2. The idea was, since the graphene oxide has a higher mechanical strength, whose band gap also is close to that of ZrO2, and it depends on which structure it comes. That is important. Would we get a better mechanical strength and a better photoluminescence? The reduced graphene oxide is something like a graphene. Graphene oxide is a highly versatile nanomaterial. We know it has gained a lot of interest from 2004 onwards. To unlock its full potential, it is often undergoes a process known as reduction, transforming it into a reduced graphene oxide. The reduction process alters the chemical composition, structure, and properties of a graphene oxide. How we do this? The reduction process. The reduction of graphene oxide involves removing oxygen containing functional group such as hydroxyl group OH, O, that is epoxy group, carbonyl group, that is CO, and carboxyl group, that is COOH group. These groups are introduced during the oxidation of graphite to create graphene oxide. The graphene oxide is highly hydrophilic and insulating. By reducing these oxygen functionalities, graphene oxide regains properties similar to graphene. A pure graphene oxide is an insulating material, whereas the reduced graphene oxide regains its properties similar to that of graphene, which exhibits a higher electrical conductivity, improved mechanical strength, and enhanced thermal stability. There are several methods to have this reduced graphene oxide. To name chemical reduction, using reducing agents, one can create a reduced graphene oxide. Thermal reduction, heating the graphene oxide to a very high temperature to remove oxygen functionalities. There are electrochemical reduction, photothermal, and laser reduction is also there. We have used a chemical reaction method to reduce graphene oxide into a reduced graphene oxide. This is a procedure of synthesis of reduced graphene oxide from graphite powder. So 1 gram of a graphite powder was dissolved in concentrated sulfuric acid. 3 gram of potassium permanganate was slowly added to that 1 gram of graphite solution under a continuous stirring for 2 hours in an ice bath. The mixture solution was kept at 35 degrees Celsius using oil bath for 30 minutes, and then we added 100 ml of deionized water. In the meantime, the chemical reaction was finished by adding 20 ml of hydrogen peroxide to reduce it from graphene oxide to reduced graphene oxide. The product was calcinated at 250 degrees Celsius, and then finally we obtained the reduced graphene oxide. We'll show a video wherein we have synthesized reduced graphene oxide. And then by taking this reduced graphene oxide, we have synthesized a nanocomposite film, that is reduced graphene oxide, polymethyl methyl acrylate, and ZrO2 nanocomposite. The stoichiometric calculation was done, and we fixed with 3% of ZrO2 nanoparticles, and we varied this RGO. Mixing the solution of ZrO2 nanoparticle in PMMA solution dropwise. In the meantime, the solutions of RGO of known weight percentage was mixed into the mixture of PMMA and ZrO2 under constant stirring for 24 hours to complete a dispersion of reduced graphene oxide into the PMMA and ZrO2 solution. Then to polymerize it, the mixture was transferred to a dish and kept it for 72 hours to evaporate solvent slowly at room temperature. Finally, we obtained the nanocomposite films. We stick to 3% of ZrO2 because we knew that the higher ZrO2 reduces the mechanical strength of PMMA, and the 3 weight percent of ZrO2 increases the mechanical strength of PMMA. Therefore, we have kept it for a 3%. And then we varied the weight percentage of graphene oxide, that is reduced graphene oxide. So this is a pure, P naught is a pure PMMA, whereas there is no ZrO2 or no RGO. This is 3%, this is PMMA and ZrO2 nanocomposite, wherein there is no graphene oxide. This is a sample where the weight percent of ZrO2 is 3%, whereas that of graphene oxide is 0.5%. And this is graphene oxide 1%, this is graphene oxide 2%. So we have varied a graphene oxide weight percentage from 0.5% to 2%. This is the experimental procedure, a video. Now, this is a very simple chemical method where we have prepared a very quality films. You can see it in a very ordinary laboratory. With the minimum facilities, we were able to produce a very high quality the polymer composite films. Now, then we have characterized this film. Now, idea was to see whether the doping of reduced graphene oxide enhances the mechanical properties as well as the photoluminescence properties. So, the graphene oxide is here. ZrO2 is in crystalline in nature, whereas graphene oxide as well as polymers are amorphous in nature. So this is pure PMMA. This is 3% of ZrO2. We can see the peaks of ZrO2 corresponding to peaks of PMMA. They are well merged. That means the incorporation of ZrO2 has happened. And then this is the case. This is in composite film. Polymer, nanoparticle, and the graphene oxide. So we can see the peak corresponding to graphene oxide as well as the peak corresponding to ZrO2 and the PMMA. The XRD pattern of polymer and ZR02 nanoparticle sample shows diffraction peaks corresponding to PMMA as well as that of ZR02. The XRD pattern of the composites, polymer, metal oxide nanoparticle and graphene oxide, different weight percent, 0.5, 1 and 2%, shows the peak corresponding to all. That means we have successfully incorporated both ZRO2 and graphene oxide into the PMMA. And they are well consistent with the reports. Now this is the photoluminescence intensity as a function of wavelength. The peak position of pure polymer, that is PMMA, is 433. That of polymer and metal oxide nanoparticle is shifted towards right side, that is 439. Then when we dope with the graphene oxide, this composite, PZ composite with graphene oxide, so the peak position has changed. Now here is the twist. In case of PMMA and ZRO2, the photoluminescence properties went on increasing as the ZRO2 concentration increases. This is probably due to the ZRO2 being uncrystalline in nature, and the interaction of this ZRO2 with the pi transition of PMMA has helped the intensity to go up. But this is not the case with this. The PZZ1, that is polymer, 3% of ZRO2 nanoparticles and 1% of reduced graphene oxide, shows the highest photoluminescence intensity. Whereas that of 2% shows the lowest photoluminescence properties or photoluminescence intensities. This is quite clear because graphene oxide absorbs these wavelength regions. When you dope with a higher concentration, obviously the photoluminescence intensity decreases. But when we compare with P0 sample or PZ3, this is the red. The photoluminescence intensity of PZ1 has increased significantly. So this shows that doping should be done wisely. So mere increasing a dopants will not increase the properties. There has to be a calculation in the percentage of the dopants. Now we looked into a mechanical strength because we are doping with a very high mechanical stress, high mechanical strength material, that is graphene oxide. These are the values estimated, the mechanical parameters of nanocomposite films. So P0 being a pure polymer whose Young's modulus is 396 megapascal. Whereas this PZZ1 this is stress versus strain diagram. From this we have evaluated the Young's modulus The PZZ1 shows a very high Young's modulus. That means its Bragg strain and Bragg stress are more than any other composites. But whereas this higher concentration reduced graphene oxide shows the lower mechanical strength. So doping, though, increases the mechanical properties as well as the optical properties, but the dopant selection becomes very important. So one should remember that dopant should be as minimum as possible. Usually the doping is 1 part in a million. If the doping concentration increases, the host material loses its own properties. So clearly, the doping enhances a selective doping, I mean to say. The selective doping enhances the mechanical properties, the electrical properties, as well as the optical properties of the composite films as well as the atomic layers. With this, I wish to conclude this session that the selective doping is significant in nanomaterials. In graphene, doping greatly reduces the carrier mobility caused by introduction of large number of charge scattering centers. In case of the composite films, the fluorescence intensity of composite samples increases with the content of nanoparticles, due to a strong molecular interaction between PMMA and matrix. PMMA matrix and ZrO2 nanopillar. In case of the reduced graphene oxide and polymer and metal oxide nanocomposites, we have seen that a PL intensity increases for a particular value of graphene oxide, as well as the Young's modulus is more for 1% of graphene oxide and 3% of ZrO2 nanoparticles based applications. So with this, once again, I thank the organizers for giving me an opportunity. Dr. Samir,
Yes, sir.
can we take the questions?
Yes, sir. Yes, sir. Definitely, sir. Dear participants, if you have any questions, please unmute yourself and you can ask any questions. If you have any questions, participants, please unmute yourself.
The main idea of this presentation was to show that any amount of doping will not enhance the properties. A selective doping enhances the properties.
Sir, in case of lasers, sir, LED and laser, they are you listening to me, sir?
Yeah.
Yeah. LED operates at lower voltages, whereas laser operates at somewhat higher voltages. Both are, work in forward bias only. And so what kind of doping strategies are done there? Because compared to LED, laser is highly efficient beam of light. In that case, how do we?
Now, it all depends. Like if you take in gas lasers, you need a higher voltage to excite them. That's a thing.
Yes, sir.
When if you take a solid laser with a high output, suppose if you want an 5 milliwatt or 5 megawatt, obviously you need to give the larger electric field to excite them. Dopants can help to modify the energy levels. But
Yes.
the intensity of a laser depends on the strength of the lasing system.
Okay. Yes, sir. Yes, sir.
I think there are no questions.
If you have any questions, participants, please.
There will be two possibilities. Either they have understood everything or they have not understood anything. Okay. Once again, let me
Definitely,
thank
sir.
Dr. Samir.
Sir, anyway, sir, you are sharing your PPT, no, sir,
Yeah, I will share
for
my
us
PPT.
to upload. Uh, anyway, this is being recorded, sir,
Okay,
and
thank you very much.
we will be uploading all these videos and to our YouTube channel, our institute YouTube channel, which will be shared to all the participants. So, dear participants, at any time you can download and you can view every session by sessions. Okay, that will be given to you. No issue, sir. I will share your contact details and all if you permit me. In case
Yeah,
of
you
any
can share.
collaborations or they may call you, sir. No issues, sir.
Okay. Once
Yes,
again, I
sir.
thank Dr. Samir for giving me an opportunity. And also I thank the Institute for organizing this online 6-day faculty development program. And thank you one and all.
We are actually privileged to have you on this day, sir. We are, and the first name that occurred to me when we decided to, uh, before when decided to file this application, the first name that came to my mind is Dr. M.D. Kumargi, sir. And
Thank you very
definitely,
much for your nice words.
yes, yes, sir. Uh, on behalf of all the participants and on behalf my personal behalf and on behalf of KLS management and my honorable principal, sir, I wholeheartedly thank you, sir, for your participation. And definitely there are many takeaways from your presentation. I hope participants will definitely have grasped all those things. And once again, sir, on behalf of all of them, I thank you, sir. Thank you personally.
Thank you very much.
Yes, sir. Yes, sir. Thank you, sir.
Now I will stop sharing, right?
Yes, sir. You can stop sharing, sir.
Okay.
The next session will be at a few minutes later. So we can.
Yes.
All right.